So the building blocks for proteins, and how do we get the identity of an amino acid? The R group, right? So we have an R group that gives us the identity of the amino acid. And then we also have, in every amino acid, we have an N and C terminus. The N terminus is N because what functional group is at the N terminus? This is the amine side of the amino acid. And then the C terminus is what? Carboxylic acid, right? Carboxylic acid. And so the R group in between the N and C terminus gives us the identity of the protein. That's attached to the, does anyone remember what that carbon was called? The Greek letter. Alpha carbon, right? So that's the alpha carbon. We'll just go through the Greek alphabet, and there if you start, you get the right answer right away. Okay, so the identity of the amino acid is given by the R group, and the R groups can be classified into different categories. Classify into different categories. And how do we classify the different R groups? Those are the levels of protein structure we have. We have the protein structure hierarchy, which is primary, secondary, tertiary, and quaternary, which we'll talk more about today when we get into polypeptides. But the way we classify the R groups is based off the physical properties of that R group, right? So the proteins fold in three-dimensional space to give us different shapes, and the way they fold is governed by the actual R group there, the specific sequence of amino acids in the polypeptide. And so what's one classification we can have for an R group if we're thinking about physical properties? I hear whispering, huh? There's nonpolar, right? So we have nonpolar. We have nonpolar R amino acids. So then we also have polar, uncharged, and then we have what? Polar charge. Polar charged. And sometimes you'll see the nonpolar split into two different ones. You have aromatic and aliphatic, right? So that just means like an alkyl chain versus like an aromatic R group in the nonpolar section. So these gave rise to the different properties for the different sequences, which then determines how the protein is going to fold in three-dimensional space. And then we also talked about stereoisomers for amino acids, right? So we have that for saccharides and polysaccharides. We had D or L or alpha or beta anomers for carbohydrates. And for amino acids, it's the same classification, meaning we have D or L amino acids. And how did we distinguish what was D and what was L? Like, what determined it? Whether what was on the left to the right. So for a polysaccharide, that was the case, but for an amino acid, remember, it was the amine group, which way the NH3 was, right? So this is given by orientation of the NH3 group. And so this was under the general term for, bless you, stereo isomers, specifically enantiomers, because they're chiral centers of each other, right? So these are chiral mirror images of each other. All right. Let's see, what else did we talk about last time? Is that where we kind of ended off? Then we started talking about the how pH affects the different protonation states of amino acids. Right, so the last thing, kind of the last slide that we left off with was the protonation state depends on the pH of the solution. I said we kind of discussed this a little bit more before we kind of moved on with this. And then the standard protonation state of the amino acid just depends on physiological pH. It's about 7.3 to 7.5 in the body, right? So that's because at that pH, that's where your actual amino acids are actually going to be existing at most of the time. So that's why it's the standard protonation state for those. And so at high pH, we said that the amino acid is going to be deprotonated, and then at low pH, it'll be protonated. But really, it's a little bit more complicated of a story because it actually depends on the pKa of that specific hydrogen that we're looking at. And so if we were just to review what pH was, right? So pH was just defined as minus the logarithm of the H plus concentration in solution. So how many hydrogen ions are floating around in the solution, and what that does is it affects the equilibrium of the protonation state of the amino acid. And so if we had a equilibrium constant, so have you guys seen an equilibrium constant before? Ka, where it looks at the ratio of the concentration of products and reactants. The equilibrium constant will be something like H3O plus, A minus, and then HA. And again, I'm not going to be testing you guys specifically on this, just to get a little idea of where this comes from. This is our conjugate base concentration, and this is our acid concentration, and these are all for weak acids or bases. This equilibrium is shifted because if the pH of the solution goes up, that means that you have a lot more of this in solution. You have a lot more H3O plus or H plus in solution. That's what actually gives you a change in the pH. So if the pH gets small enough, right, it'll then start shifting the equilibrium to then have more of the HA. And so this would be the protonated form of your amino acid, for example. So I'll write that right here. This is the protonated form of amino acid, and this is the deprotonated form. Right, and this value over here is the same for a given temperature. Right, so if we keep the temperature the same, Ka needs to stay the same. Right, so if Ka stays the same and we change how much H3O plus is in solution, then this number, if you're making the numerator larger and larger, you have to adjust these values to keep that number the same. Right, you're kind of like adjusting them to kind of always make sure that this stays the same. And so as we drop the pH, you're going to start to favor the protonated form because there's already so much H3O plus in solution, and law of mass action, if you guys remember Le Chatelier's principle, will push the amino acid to then be protonated. And so this is for a generic weak acid or weak base that we have a relationship. For an amino acid, we can have a lot of different protons. Actually, we have 2 on every amino acid that can fall into this category. So we have the amine proton, right, on the amine side, the N terminus, and the carboxylic acid terminus. And so depending on the pH, the amine and the N-terminus and the C-terminus can either be protonated or deprotonated. And that's related to the pKa value. So this is for a given hydrogen. Right, so we can look at each hydrogen on the amino acid or in general any molecule, and we can determine how acidic that hydrogen is. So you may have heard that term before. How acidic is this hydrogen? It's looking at the pKa value, and based off the pH, is it likely to be protonated or deprotonated? So this is asking how acidic is this hydrogen? Or like how likely is it to make H3O plus in solution? Right, so pH is important, especially for a lot of biological functions, so things like different lysosomes and stuff maintain a low pH in there to, keep catalytic activity at certain levels. So maintaining pH is really important for a lot of biological processes. Okay, and so the pKa is just equal to minus the log of the Ka, right? So that's all the pKa is. You guys may or may not have seen pKa. It's not, terribly important to understand this equation, but that's where this comes from, right? So this ratio, right, this number that always is going to stay the same for a given acid, right? If you take the log of that, that kind of tells you how big this ratio is. And so that's why this value tells you if it's likely to be protonated or not protonated, depending on the pH of the solution that you're in. Okay, so I know that's a lot of words that I just threw. So any questions on that? It'll be a little bit more clear. It's actually in practice, it's not as complicated as I'm making it sound right now. How you determine the protonation state of a amino acid. There's probably a little bit more detail and background than usual. Okay, so if we look at a specific example, so use glutamic acid down here. Basically, if the pH is less than the pKa, then the protonated form is favored, right? And so as we get to lower pHs, right, that means there's already so much H plus in solution, or H3O plus, that it's favored to have the proton on the amino acid. It's taking it away from solution. If the pH is greater than the pKa of that proton, then the deprotonated form is favored. All right, so like I said, that was a kind of a long, lengthy explanation, but really the only thing that's relevant is just these two bullet points right here, right? If the pH of the pKa is less than or equal to the pKa, the protonated form is favored, and if it's greater than or equal to the pKa, then the deprotonated form is favored. So depending on the amino acid, we always have at least two acidic protons or basic protons on there, because the C-terminus and the N-terminus always have that. So even in a long protein chain, for example, eventually you reach two edges, right? So when you reach those two edges, you're either going to reach a C-terminus or an N-terminus. But certain R groups also have acidic protons on them too, right? So glutamic acid, as the name would suggest, has an acidic proton in the R group of it. So let's look at neutral pH. Neutral pH is what? 7. Yep, pH is equal to 7. And so we're going to compare this value of the pH with the pKa's of the different amino acids. And then from there, we can determine what the protonation state will be, right? So a typical question for something like this is, here's an amino acid, draw the correct protonation states based off the pKa values that are given to you. Okay, so for glutamic acid, we see that this right here, what part of the amino acid is this that I just circled? So this is a carboxylic acid here. Is it the C-terminus, the N-terminus, or the R group here? So there is a carboxylic acid on the C-terminus, right? However, this is an R group because there's a carboxylic acid right here, and the carboxylic acid that's right next to the amine, this is the alpha carbon right here, and then this is the anomeric or carbonyl carbon right here, right? So that means that this whole thing is going to be the R group, right? And the R group gives us the identity of the amino acid, and so this amino acid is called glutamic acid, right? So that's the fact that it has acid in the name of the amino acid tells us that it probably has an acidic R group, right? So it's basically 1, 2, 3 carboxylic acid. So if it was just a regular carboxylic acid alkyl chain, what would the name of it be? So if I was to just draw the molecule like that, 1, 2, 3, what would the name of that molecule be? Propanoic acid, right? So this would be propanoic acid. I know it feels like we're really far into biochemistry. However, next week, that's everything that I just talked about is going to be on the exam, right? So we're not quite out of the woods yet with organic chemistry, and I don't know if we ever will be. I know I'll never be in life, but you guys, maybe it's just a couple more months and you'll be done. Okay, so this is the R group right here, and the pKa for this proton is 4.07, so that's pretty low. So at a pH of 7, is this going to be protonated or deprotonated? Right, so if the pH is greater than or equal to the pKa, oops, forgot like half the letters there, pKa, that's this right here. That means that we get the deprotonated form, right? And so what's the pKa? 4.07, right? That's this value right here, 4.07. And what's the pH of the solution? 7. So is it greater than or equal to or less than or equal to? The pKa is less than, oh, I flipped. No, I did it the right way. So the pH is greater than the pKa, right? So the pH is greater than, if you're saying in your head that the pKa is less than the pH, then that also makes sense. So 7 is greater than or equal to 4, which means that the deprotonated form is favored. All right, so if we think about this, that means that the pH of the solution is higher than the equilibrium constant, the logarithm of the equilibrium constant for that proton, which means to keep that ratio the same, it's going to get rid of the proton. It's going to put that proton into the solution. Right, so like I said, that's, a little challenging to wrap your head around that concept, especially the first time seeing it. The important thing is just remembering these relationships. If you know that the pH is a certain value and you're given a value for the pKa, you can determine if it's protonated or deprotonated. So that means that this carboxylic acid group turns into what? Carboxylate, right? So we get now the minus charge there, and so it's the deprotonated form. Form is favored. All right, and we have 2 other protons on this one. So this is just one of the protons that we're looking at right now. So now let's look at the C terminus, right, which is over here. The pKa is 2.1. So is it going to be protonated or deprotonated? It should be deprotonated, right, because the pH is greater than or equal to the pKa. 7 is greater than or equal to 2.10. So that means it's deprotonated. So the carboxylic acid group turns into a carboxylate. And then now let's look at the amine group, right? So the pKa for that is 9.7, right? Is that greater than or equal to 7? It's greater than, so the pH is less than or equal to, let's do that because it's a little easier, less than or equal to the pKa, which means that this is going to be protonated or deprotonated. It'll be protonated. So it'll be NH3+. All right, and kind of a good rule of thumb is that amines are more likely to be protonated at neutral pHs, and the acids, they need to be, at neutral pHs, they're likely to be deprotonated. so the carboxylic acid side of any protein or amino acid is generally in the carboxylate form, because you can see that's a very acidic proton right there, because it's tied to that amide group, and that whole amide group is very electron withdrawing. So it's actually pretty happy staying in this form right here. So that's why that number is so low, which means that this is almost always going to be deprotonated. If you were to basically you'll never see that pH in the human body. Okay. Does that make sense? Right? So you're just looking at each of these and then determining what the correct form of the amino acid, or what's the correct ionic form of the amino acid based off the pH of the solution. So that's what affects you. And so why is that important? Well, if the R group is charged or not charged, a whole charge on something really affects how it interacts with other things, right? So let's say you drop the pH of a solution that you had catalase in that we've dealt with before. You drop the pH, all of a sudden you charge half the R groups or something like that. Now that's going to really disrupt the structure of the protein, because if you have a bunch of charged R groups, they either want to be attracted to other charged R groups or repel from other charged R groups. It affects a lot of things when you change the pH. So that's why pH controls protein structure a lot. Okay, so then why don't you guys take a second for each of these amino acids, draw the correct form of them in the correct protonation state based off of the pH of the solution. So these are the pHs of the solution that they're in, and then each proton has a pKa value that's associated with it. All right, is anyone still working? Okay, all right, so let's look at the first amino acid. It's going to be tryptophan. So for this amino acid, for the R group here, we have an interesting looking R group. It's an aromatic ring on top of a couple heterocycles in there, meaning we have different atoms besides carbon. But it does have an amine group in the R group that can be protonated or deprotonated, right? So this nitrogen right here can be protonated or deprotonated. Right now it's shown in its neutral form, so it only has 3 bonds to it. And the pKa of this nitrogen is 6.04. So is the deprotonated or the protonated form of this favored? So the the pH for this one is going to be greater than or equal to the pKa, right? So if the pH is greater than, then it should be the deprotonated version of the amino acid, right? So it'll stay this way. So this would be an uncharged amino acid side group, right? So that's fine the way it is. What about the N-terminus of this molecule, right? So if we circle or highlight this whole area right here, this is the N and C terminus of the molecule, or of the amino acid. In this whole group right here, that's going to be the R group for our amino acid. So this one has a pKa of 9.33. So is it protonated or deprotonated? This one should be protonated, right? So the pKa, or the pH, is less than or equal to the pKa. So this has to be protonated. So protonated, and then this is deprotonated. No, because you don't take an H away when you're looking at the amines, right? So when we're protonating or deprotonating, it's going based off of, for an amine, you want that you're comparing it to the neutral version of it, right? So you're protonating the neutral version for an amine, technically because it's a basic hydrogen. It's not acidic because the pKa values are usually on the higher end for these ones. But you don't take that away because then you put a negative charge on the nitrogen there, which you can have, but when you're looking at amino acids, you're always protonating the amines in our case. Okay. Mm-hmm. And then the OH, for example, that's why when you in the protonated form, it's in the OH form. It's not in the OH3, for example. If you put does that mean that, that means that
Why does
if
it
we're not
not
influenced by the
change
pH of the solution, this is what the molecule is. So we only really, because nitrogen itself can form 4 bonds, and it's okay stabilizing 4 bonds like that, having a total positive charge on the molecule,
So we
or
only,
the atom.
so we only add protonation to NH2.
Yeah. If you ever see amines, those are going to be positively charged in their ionic form, and the OHs, or the oxygens, will only ever be negatively charged. Like I said, it is possible to have a negative charge on nitrogen, but in general, it's not very likely. But that's actually a really good question. The amines, we're going from a neutral state to protonated, and then oxygens too. Question?
What's under the N? Is that a plus?
Under the N, oh yeah, that's a plus sign. That's because I added a proton there, and so now that whole N terminus is positively charged.
Okay, so would you change it to NH3?
Yeah, I just put an H over here, but I could have done that too. So if I put NH3 there, that would be the same thing. Right, and we think ammonium is a very common ion, and it's NH4. So nitrogen is usually okay accepting an extra bonding partner to have a positive charge on it. Yeah, that's a good question. And then for the carboxylic acid, or the C terminus of the molecule, is it going to be protonated or deprotonated? It'll be deprotonated because the pH is greater than or equal to the pKa. So it gets deprotonated. So this becomes O minus right there. Okay. Any questions on the first tryptophan?
Why do you remove the H from the OH but not the NH?
Because the nitrogen isn't going to, when we're talking about going from protonated forms to unprotonated forms, the nitrogen is never going to lose the hydrogen to become negatively charged. The oxygen, it has to do more with the actual structure of the molecule. Like, this is a very stable structure right here. We talked very, very, very briefly about resonance, and this is resonance stabilized. And in general, oxygen is going to lose a proton to become negatively charged, and nitrogens are only going to gain a proton to become positively charged. Like I said, it can happen that you lose this and it becomes negatively charged here, but chances are you get rearrangement in the ring and you have a reaction happen. In general, the amine groups in most molecules, they act as bases, right? So remember when we talked about organic acids and bases, amines were the bases, right? And that's because if you think about definitions of bases, they're hydrogen acceptors, right? Acids are hydrogen donors, bases are hydrogen acceptors.
So even if it's deprotonated, you just leave it how it is.
So when it's if it's in its deprotonated form, that means that it's left in its neutral form.
And then if the oxygen is in a protonated form, or the OH is in a protonated form, you just leave it as well?
Yeah, if for example, the pH was, 1.2 or something here, you leave the H on the OH.
1.2.
If the pH was 1.2,
Oh,
right? So if the pH
yeah,
of the
yeah.
solution was 1.2, then you leave the hydrogen on there, right? You don't add another hydrogen to the OH group.
Because then it would just be one.
Yeah. I get it's kind of confusing because you're starting from somewhere, and if you're starting from there, you're saying, how do I add or remove from the current structure to what you're getting at? But really, there's only 2 options, right? It either has OH or O minus. This is either going to be NH or NH2 right here, or this will be either NH2 or NH3 right here. Those are the 2 options that are in the equilibrium here.
If that had been NH, would it also stay because it's
This one? This, so you won't find this.
can't
NH.
lose? Okay.
Yeah, you won't ever find.
Not as
Yeah, you won't ever find something like an amino acid that has an H minus, and that's your R group right there. You won't ever find that. This'll be end up being so basic that it'll pick up another hydrogen no matter what from water. It'll rip it off of water. Okay. It's the equilibrium that you're looking between these two. So if you looked at tryptophan here, it would. And where was the other nitrogen? This one. And how many? So it would be, if we're just focusing on this group right here, the equilibrium is between that goes up there. It's between these two is what the R group is looking like. This is what the equilibrium is looking like when you're looking at that equilibrium constant. So this would be like, really, if we're thinking about acids, it's HA and A minus, which is what you see with the carboxylic acid groups. They go from protonated to deprotonated. With bases, really what you're looking at is B and HB plus. So that's where the confusion. Basically, you can look at everything from either perspective, and it all works out the same. But when you're looking at an amine group, an amino acid, you just have to realize that you're going between the form that's right here and adding a hydrogen into that. When you're looking at oxygens, it's either the carboxylate ion or the carboxylic acid. That's the equilibrium that you're going between. That's what this pKa is talking about, the exchange between these two. Because something like this, you won't ever see. This is way too basic of a molecule. It'll rip a proton. It doesn't exist. It's like when you put hydrochloric acid in water, it's a strong acid, so it dissociates completely. This would be a strong base. It would create OH minus completely if you put that in water. Okay, so I'll make a note of that. Nitrogens / amines go between NH2 and R NH3 plus. Oxygens go between R OH and R O minus. Right, that's what the equilibrium is talking about. Based off of the pH value of the solution, do I have this form or do I have that form? Okay. All right, so let's look at the second molecule here. We have isoleucine. In here, the only two acidic or basic protons are going to be the C terminus and the N terminus. The C terminus and the N terminus, right? So this kind of adds into the question, like, why don't you see, you know, the NH group, NH3 group, or NH2 group getting deprotonated ever? It's because if you look at a molecule like this proton right here isn't going to be acidic. If you put it in acidic solution, it's not going to donate that proton because it's such a strong bond between that and carbon that if you took away that proton, it would be such a reactive molecule that you wouldn't actually see it exist ever. So it's the same thing when you see something with a negative charge on the hydrogen or the nitrogen here. It'll just pull a proton from the water in the solution and it won't actually see something like that. So here the only two groups that are going to change are the N and C terminus. For the N terminus, we see that the pKa value, I feel like I actually flipped these values. All right, whatever, we'll do it with this. The pKa value is 2.32. That looks more like a carboxylic acid pKa value. So it's 2.32. Is that greater than or less than the pH? It's less than, right? So the pH is greater than or equal to the pKa, which means that it's going to be in the deprotonated form, so it would stay the way it is. And then if we look at the carboxylic acid side, which has an unusually high pKa value for the C-terminus, we see that it has a pKa value of 9.76. Is that greater than or less than the pH of the solution? It's greater than, right? So the pH is less than or equal to the pKa, which means it'll stay in the protonated version. So in this case, you wouldn't make any changes to the structure. That's because the pKa values I have up here, but chances are those values are actually flipped. And you still have a neutral molecule, it's just you have a positive and a negative charge on the molecule. Okay, and so let's look at this last one. So here we see we don't have a carboxylic acid group, but this proton can be thought of as being pretty acidic here, right? So the reason are, for an alcohol, right? Because alcohols tend to not be acidic. They don't create H3O plus when you put them in solution. But this one, for some reason, does have a relatively low pKa value compared to other alcohols. And that's because of this aromatic ring right here. If we donate this proton, it can be stabilized by this ring right here. So this is an amino acid that actually has an acidic proton attached to a hydrogen that's basically stabilized by the aromatic ring right there. So most alcohols aren't acidic, but this is one of the cases that it is. And so that would be a phenol group. Okay, so the pKa value is 10.46 and the pH of the solution is 12.0. So the pH is greater than or equal to the pKa, which means that, do we have the protonated or deprotonated version? We have the deprotonated version of this. So we get rid of the hydrogen, and because it's an oxygen, that means we get rid of the hydrogen, put a minus sign there. If we look at the N-terminus, the pH is greater than or equal to the pKa. And so that means we also have the deprotonated version, so this is going to stay the same for the amine side. So this is one of the few amino acids that's negatively charged at neutral pH even. Sorry, at a high pH like this. And then the carboxylic acid group, the pH is greater than or equal to the pKa. So then it's going to be deprotonated. So this goes from OH to O minus there. So if it was an exam or a quiz, I'd probably just have you redraw the molecule in the correct protonation state for all of the groups here. But this would be like a typical type question. What is the protonation states of all of the either amine or oxygen hydrogens in the amino acids? And again, this is important just because if you have charged side groups, depending on the pH of the situation, that determines the function of the protein because it changes how the structure is assembled. Okay, any questions on that? All right. Okay, so the last thing for amino acids, I believe this is the last slide, is something called the isoelectric point. And so the pH that the amino acid exists majorly or majority as what's called as a Zwitterion is called the isoelectric point. So has anyone heard Zwitterion before? Okay, so what the Zwitterion is it's just a molecule has positive and negative charges on it. But is still neutral. The Zwitter ion? Or which one?
Yeah,
The very top one?
yeah.
The Zwitter ion. I don't know if that helps when I say when I say it like that, but I'll Zwitter ion. This is it's a goofy sounding name, but it's just a molecule that is an ion, but the net charge is still 0 on it, even though it still has positive and negative charges on it. Basically, what it means is that you have enough positive and negative charges that they will cancel out with each other. And the isoelectric point is just the pH that you're at the Zwitter ion form. And so the way you calculate the isoelectric point is this: you just take the pKa. For example, if you have 2 amino acids, or sorry, 2 acidic protons, the pKa of each, and you divide it by 2. Right, so if you have, for example, we had isoleucine on the previous slide that had only the N-terminus and the C-terminus, the pH at which you have equal amounts of both the protonated form of the N-terminus and the deprotonated form of the C-terminus, which is the pH right between those 2 pKa values. That's the isoelectric point there, because you'll have both a positive and a negative charge. Although I think I wrote the wrong pKas for that one. So for example, if we have methionine and this is our amino acid at neutral pH, right? This is a Zwitter ion because we have the positive charge on the N-terminus and the negative charge on the C-terminus. And so we have charges on our molecule, but the total charge is still 0 because -1 and +1 cancel out with each other. And if this was a pKa of, let's say, 2.1, and this one was a pKa of 12.2, then the isoelectric point is just equal to pKa 1 plus pKa 2 divided by 2. And so that would give us 14.3 divided by 2, 7.15. Right, which is really close to neutral pH. So methionine would be a Zwitter ion at biological pH, most likely. All right, and because this has to do with the equilibrium of going between the protonated and deprotonated forms, if you're slightly above or slightly below the isoelectric point, that doesn't mean that you don't see the Zwitter ion at all. It's just this is the optimal pH that you'll see majorly the Zwitter ion form.
We just always go left to right for PKA 1.
Oh yeah, so you're only going to be looking at, in this case, I'm probably not going to give you anything that has a charged amino side group to calculate the isoelectric point. It's really the 2 pKa values that are closest to each other. On most amino acids, especially neutral ones, It's just gonna be the N terminus and the C terminus. But you could add it in any order and it wouldn't matter.
That's true.
Mhm. Okay. All right, so let's take like a 5-6 minute break, and we'll come back and we'll start talking about protein structure, hierarchy of structure, and then a little bit about enzymes if we get to it today.